So welcome everyone. The speaker today is Paul Bendich, and the title is Data Complexes, Obstructions, Persistent Data Merging.
Thank you all very much. Thank you for the invitation. I've never been able to make these because it's conflicted with teaching, but now the summer started, I'm hoping to be a weekly attendee. So let me go into full presentation mode. Everyone see this okay? So I came up with the snappy title when I realized that the previous title of our paper was a bit boring, but this talk is about a paper called Persistent Obstruction Theory for a Model Category of Measures with Applications to Data Merging. And my co-authors are Abe Smith and John Harrer. I have two affiliations. One is at Duke in the Department of Math, and one is at this company in downtown Durham, Geometric Data Analytics. And believe it or not, this work was entirely at the company, although it's probably the mathiest thing we've ever done there. So here's the talk in one slide. And I should say, I've learned to do this from DARPA projects where you kind of have the idea that you have one slide and then they stop listening. So here's the one slide, and then everyone is entirely free to stop listening. Or if you wish to be bored, you can listen to the rest of this talk. So what we do is we establish what we think is a useful mathematical foundation for database merging, database aligning, database joining. In particular, the problem we really tackle is the idea of you've had a bunch of different databases, you've merged each of them, say, pairwise in some local fashion, and then you're having trouble figuring out how to merge all those mergers. And this is a problem that people actually encounter across the world in database engineering. And the usual DARPA idea of you tell them what people currently do now and why it's not that good. Currently, people use semi-automated data alignment tools. There's a really nice state-of-the-art tool out there called Hummer. It's really nice in that it has very nice user interface and is very pleasant to use. And essentially what it does is says, okay, you tried to merge these databases. Maybe you screwed up on this one was first name, last name, this one was last name, first name. Maybe the person you thought was Paul over here was Abe over here. Maybe here are a few ad hoc algorithms for particular mess ups that people might do. Do you want to apply them? So they're essentially user in the loop, semi-automated. We build a theory using a lot of fancy mathematics. And again, for these sort of DARPA projects, the fancy mathematics is fine, but is it useful? So the fancy mathematics involves simplicial sets, which I'll confess I knew very little about when we started the project about 2 years ago. Measure theory, obstruction theory, so a la Steenrod, how do you find obstructions to sections, and persistent cohomology. And the improvements you get over something like Hummer are you get to be able to automatically detect whether a previous set of mergers is inconsistent. In other words, you merged all these local databases this way, and now it's going to be inconsistent and you detect them, but basically by an obstruction cocycle. I should pause to say, by the way, that please do interrupt me with questions, but I think the way I've set it up, I don't actually see the chat window. So if there's anything in the chat window that's essential, Henry or Sarah, please interrupt me. You also get what we call automatic merger repairs to create potential consensus. So in other words, if someone down at the branch office screwed up and this particular merger was a bad idea, you're able to say, if we could only convince them to fix it this way, we could get the merger as we go. For those who have seen Norman Steenrod's obstruction theory, this is what we often call Steenrod's trichotomy. Basically, there's an obstruction cycle, cocycle. Either it's zero, in which case you're cool, or it's not zero, even in terms of cohomology, in which case you're doomed, or it's not zero as a cocycle, but is zero in terms of cohomology, in which case you can do this sort of thing we call merger repair. And a lot of the mathematical contribution we make is to show that you can actually phrase the database problem in the language that the Steenrod hacker can then kind of come down and do it. Where persistent cohomology comes in is we're able to, and this is really, I think, very novel for people doing this database merging problem, we're able to define a notion called approximate join, where you say, here's one data table, here's another data table, here's something that approximately joins them and allows the notion of fuzzy consensus. That's where the measure theory is going to come in, and it's going to come essentially with Wasserstein distances between each. So that's the talk in one slide. The preprint is up on the, actually, I should say, the paper has since been published. So this is in Transactions of the AMS. So you can see I've adapted these slides. But the preprint is also up on the archive, and I think that's actually the version we published minus some decorations. It's with Abe, who's from Geometric Data Analytics and Wisconsin Scout faculty member, me and John Hare. The interesting thing about this is that with these DARPA projects, they often assign to you a very, very focused, almost referee who kind of harasses you over the years of the project and sort of looks at drafts and really edits the hell out of them and tells you they're not good and tells you how to make them better. It was this guy called Tony Falcone. I feel extremely bad about the fact that he's not an author on the paper. I think the amount of contribution he did by just sort of making us make it better deserves authorship. The rules of the game were that he sort of was on the government side, and so that would be a conflict of interest. But every time I give this talk, I say I think he should be an author. And then we had a lot of help from very early stages from Jose Perea and Justin Curry. Really nice stuff from Greg Friedman and Jonathan Mattingly with a lot of the measure theory. And this was paid for by the Simplex program. John Paskovitz was our DARPA project manager. Okay, enough of that. So here's the talk outline. First, I just want to kind of walk you through a little bit of intuitive pictures about what we're trying to do. Then I want to define our main object, something called a data complex. What's hiding in the background here, and I think I put this in the abstract, is there's a model category going on. I've kind of omitted that. It's in the appendix of the paper, and I'm happy to go some of the language there if it's useful to people. But I think it's more fun to explain it more intuitively. But these are the basic objects we're going to be talking about, something called a data complex. Then there's two main theorems, and sort of interesting the dichotomy here about what mathematicians care about and what other people might care about. The first main theorem is very hard to prove, at least, for someone as weak as me. In other words, it's a theorem that says that we've actually modeled the database merging problem correctly with all of our tools. So there's something called the Kahn condition for simplicial sets. And it turns out that the Kahn condition for simplicial sets is going to be equivalent to, is going to help us with the idea of proving that joins are possible. So that's a hard theorem, which essentially just says that I phrased a problem that people care about in mathematical language. It'll then be very easy, I would say mathematically, to just build a persistent obstruction theory on top of these things called filtered data complexes. The second main theorem, which is mathematically trivial to prove, it's basically just a translation of stuff Norman Steenrod did in our new language, is the thing that I think database engineers will find useful. It's the one that gives these improvements here. I find that distinction interesting. This is 5 pages in the paper and there's a lot of blood and tears. This is a thing that is, the theorem 2 is immediate, but it's much more interesting to people who are not me. Okay, so here's the problem. Imagine you've got some data tables. So imagine you're in different branch offices, and here's, say we have name, age, and age weight. I am turning 42 on Monday, and so you can see how long we've been working on this problem. And we'll leave comments about the weight aside. So we have name, age, and age weight. And suppose those are my tables, and I want to merge them in some particular way. So I could say, for example, all right, I want to go to name, age, weight. There's some guy called Paul, he's 38. The person who's 38 weighs 200. That sounds like a reasonable merger to me. But here's another table over here, which is name and weight. And there's someone called Abe, he's 182. There's someone called Paul, he's 200. And so maybe I want to merge the age weight and the name weight table. And that seems reasonable. The person who's Paul is, I want to join, and for people who use SQL language, I might want to join them on weight. So the person who's Paul is 200, the person who weighs 200 is 38. So that's a reasonable merger there. And so I can merge, now over here, can I merge name weight and age weight on weight? Not really, because the person who's Abe is 182. There's someone who weighs 181 who's 36. Maybe I can join those if I have a notion of approximate join. So lots of reasons why this is hard. You could have conflicting data, you could have duplicate data, you could have accuracy variation, so on and so forth. This is a fun thing to Google, by the way, Hummer, which is a thing that people can buy, lots of businesses use it, and is, as I said, semi-automated alignment tool. Okay, so sometimes you have a problem, and you'll notice I'm starting to draw these pictures. You should always feel there's something abusive when people draw things, right? Because what am I modeling? How do I have a right to draw it? I'm drawing pictures to suggest sort of sections, obstructions to sections, things like that. A lot of the hard work we did in this paper was actually showing that I had any right to draw this. In particular, the reason why simplicial sets are going to be important rather than just simplicial complexes and things like that is there's no actual geometry. I have no idea what it means to be 1/3 of the way between the age vertex and the name vertex. And we spent about a year being steering ourselves wrong in this paper, in this project, by trying to make that actually make any sense. So there isn't actually geometry downstairs, just combinatorics, and that's going to make things more interesting. But I might have, for example, this thing age, name, weight down there, and when I look up here, I said, okay, maybe one entry in my table is 38 Paul 200. Maybe one entry in my table is 38 Abe 181, weight 82. Maybe those are the same. That's where persistence is going to come. So, for example, you could do that sort of merger. If you said that 200 and 182 were close enough to each other, now all of a sudden you have lots of potential mergers. That's where the approximate merger is going to come. Sometimes you have global obstructions. So, for example, it might be that the way the things were set up is there's a name weight table where there's someone who's called Paul who's 182. There's someone who's called Abe who's 200. There might be a name age table where someone called Paul who's 38, someone called Abe who's 36, and there might be an age weight table where there's someone who's 36 and weighs 182, and there's someone who's 38 and weighs 200. And now all of a sudden you see the problem that you're not going to be able to take that and somehow take those two local mergers. I can easily merge name age with name weight on name. I can easily merge age weight and name weight on weight, and all that seems respectable and fine. But somehow the global merger of those three local mergers looks impossible. And that obstruction sure smells like a Mobius band, the sort of classical obstruction thing that's going to go wrong. And so a lot of the work in the paper, what this made this applied math, was finding a way to model this problem so you could just say, no, dummy, you have a Mobius band. There's an obstruction cocycle. It's not going to work. And if you thicken things up in various ways, maybe it will work. So, for example, if I say that 200 and 182 are the same, it's going to be fine. If I say that 38 and 36 are the same, it's going to be fine. Somehow, if I say Paul and Abe are the same, I don't know quite what that means, it's going to be fine. But actually, that last part isn't so silly. You could imagine people might have different nicknames. So you might have some metric on names as how likely they are to be nicknames for each other. Or maybe there's Paul in one and there's Dr. Bendich in another, or some nonsense like that. So that's the story intuitively. Now let's set up a lot of mathematical machinery to make it make sense. So I should say, by the way, that here's how I want to describe it to someone who's a database engineer. To a database engineer, what they want to do is they want to take table 1 and table 2, and they want to join them. This is sort of SQL speak, but you can imagine lots of other speak that's kind of simpler. You might want to say, I want to join table 1 to table 2, identifying column 1 from table 1 with column 2 from table 2. So name weight and heaviness age. Let me join where I say that weight in column table 1 is the same as heaviness in table 2, right? And that's the join I want to make. What you're going to demand of a database engineer, here I'm phrasing this as if it's sort of applied math as we're building towards software, which we actually are trying to do right now with the company to make this usable, is what I'm going to ask the database engineer to do is tell me what attributes they find interesting. So they're going to choose a set of attributes like name, weight, age, shoe size, blood pressure, whatever. And for each attribute in the set of attributes, they're going to declare a value space. So they're going to tell me what particular set of values that attribute can take. And they're going to give me some metric on it. And I'm going to insist that this be a compact metric space, which is incredibly reasonable. And then these are sort of the things that the database engineer might want to do. Again, please, I might be going a little bit fast, so please do interrupt me at any time. Check the time. Okay, so now here is some actual combinatorics and some math. We're going to say that an attribute list of length n plus 1, is just a function from 0n to n. So there's my ordered list. And I'm going to consider script A to be the set of all such attribute lists, where script A sub n is all the ones of length n plus 1. I have face maps, which map an attribute list of length n plus 1 down to an attribute list of n minus 1, where I just omit the ith entry. So that's exactly what you'd think of, just take a triangle, map it down to the edges by face maps. I also have these things called degeneracy maps. which map an attribute length of length n plus 1 to an attribute list of length n plus 2 by just repeating the ith entry. So for example, I have the edge name weight, and I make the degenerate triangle name weight weight by repeating that. That sounds silly. That's needed in simplicial set theory. It's also entirely reasonable later when we're going to see what we mean by measures. It might well be that what I really mean by name weight weight is I have weight according to one opinion and weight according to another opinion, right? And so that might be what's going on. The claim, which is quite easy to prove, that this structure, ADS, is an augmented simplicial set. For those who haven't seen that, there's a really, really nice 93-page or so survey article by Greg Friedman called An Elementary Illustrated Introduction to Simplicial Sets. It's really beautifully written. Greg is also incredibly generous with his time and spent a lot of time chatting with us about notions. So it's really wonderful to read. And all it really means is that you have this combinatorial object, and the face maps and the degeneracy maps kind of play in the way you want them to play. For those who haven't seen simplicial sets, by the way, I think to really emphasize is that they're always infinite. Because if I have a triangle, I can always just repeat edge, edge over and over and over again. There's always these sort of infinite combinatorial objects, but you can sort of see them the way you see them. Okay, so what's a data table? A data table is, let me take an attribute list T, like name, weight, shoe size, and let me consider a finite measure on that. So that's something that is going to generalize very much the idea of humans call a table. So just a measure on that. So for example, a row in a table that humans call a table could be thought of as an atomic measure just on one particular entry in the product, like Paul 38200. A data table with 5 rows might be just a sum of atomic measures. But you can fuzzy things up and make them measures. You could do something like, if I have weight and height, but I only tell you my height, which is 5'7", and I don't tell you my weight, you could say that's the measure, which is 5'7" cross the distribution of weights for American males who are 5'7" according to the census, right? And that's another data table. There's our value space, and then we look at this metric here. We actually use the max metric for technical reasons, which we find annoying. We can't prove things with other things like that. Let's consider what we call the ambient data complex over the attribute space. Those are all the data tables you could possibly dream up in all of your fever dreams. Every possible data table is massively infinite over all possible attribute lists you have. You can stratify this by dimension, just as we had before. And we get a simplicial set structure. So if you have a data table of size n, you can map that down to a data table of sign n-1 by just doing a marginalization integral out. We have degeneracy maps. So if you have a data table of size n, oh, and this is a typo, that should be n+1, not n-1 on the degeneracy map. I apologize. It's amazing I haven't caught that. You just do a diagonal Dirac duplication up as you go. So you could phrase that in different language, but sort of the obvious thing we would do. Theorem, or proposition really. This is an augmented simplicial set as well. The proof uses Fubini-Tonelli to talk about how you can iterate various integrals and bookkeeping. Not hard at all. Okay, so I should probably speed up a little bit. Let's see what time it is. Yeah. Okay, so now let's talk about how to actually set things up. So given an ambient data complex, a data subcomplex is a subset. It turns out this is a subcategory. I'll leave that out. That's closed under base and degeneracy maps. And then you take the simplicial map, you get an attribute base. So really what you're thinking about here is a data subcomplex might be, for example, the data you currently have. So you have these following tables. You take all things that happen under degeneracy maps and face maps. There's your data subcomplex. It's what I have right now. We can talk about something called a data section. And now we're going to start getting to the obstruction theory. So if you have your base downstairs, you have the data tables you currently have upstairs, and you're sitting inside some ambient thing, which is all the data you could ever possibly dream of. A data section is just sort of what you might imagine it is. So for example, a data section up here might be 38 Paul 200, 36 A 200 or so. The reason we like data sections is we can start talking about what we call the extension problem. For those who have seen obstruction theory, this is now a familiar problem. So if I have a section defined on, say, the boundary of something, for example, the boundary of the thing downstairs, the one cycle that goes age, name, name, weight, weight, age, and I have a section that maps upstairs, can I extend that to the interior? That's the merger, that's the merging the merger problem, right? Because if I have a section downstairs on the circle, that means I've managed to successfully merge age, name with name, weight on name. I've managed to successfully merge name, weight with weight, age on weight. And I've managed to successfully merge age, weight with age, name on age. Cool. Can I merge all those suckers to make a beautiful global table on age, name, weight? And that's an extension problem. For those who don't see instruction theory, we're now in nice words. So basically just phrasing it this way, considering a data subcomplex of an ambient, if I have a simplicial map taking the n skeleton downstairs, in this case that I'm talking about, n would be 1, that says each table, each attribute list downstairs gets a table upstairs. Does there exist an extension? And hell, let's just go all the way to an plus 1, as in if I had more data, in this case a and b are the same, that agrees with what I had before. That's the problem. And if not, and here I should say everything up to this point, this is sort of classical Norman Steenrod. We're just translating it into this new language and making it applied math. Something that Steenrod didn't think about, because their persistence wasn't in his bailiwick. What's the minimal distance that would allow that extension? So in other words, what do I mean by an approximate measure? Okay, so back to reality. And I think in interest of time, I'm going to skip through the next few slides. The point about all this, and this is bookkeeping in the paper, is that there's a nice way to talk about all of these mergers that actually make sense. So there's a way of saying, I want to include one data attribute list into another, and there's a well-defined notion of merge. There's a well-defined simplicial set model category language that I can use to say, if I have two data tables, T01 and T02, I have something included T0 into one of them and something included T0 into the other one. There's a well-defined notion of a merged table that actually respects those sets. So in other words, I can phrase in this simplicial set language exactly this SQL command in a well-defined way. So I won't really get into it, but that's for those who are interested in the model category voodoo, these things called data complexes are basically simplicial sets with this extra notion, which I think is often pretty interesting. But I'll leave that out for a second. Okay, so now we're going to get into where a little bit of the first fancy theorem gets in. So here's what we mean by joins. If I have two data tables, T01 and T02, sorry, two attribute lists, T01 and T02. So for example, age, weight, and age, height. And I have something that they have in common. That's this inclusion of T0 into both of them. So for example, age, height, and age, weight both have age in common. I'm going to consider the merged attribute list that I just half defined on the previous slide. And suppose I have data tables over T01 and T02. So what that means is over age, height, I have some measure. It could be, as I said before, the nice thing about this notion of a data table as a measure is that could be one entry. Hey, this is Joker poor Paul, who's 200 pounds. Or it could be a measure over that. Who knows what it is? It could be lots and lots of entries. All those are data tables. Given a data table over age, weight, and a data table over age, height, I'm going to consider all the possible joins of them. So what do we mean by that? That's all possible tables, tau 0, 1, 2, over the merged attribute list, age, height, weight, which marginalize exactly correctly down to those two things. So that's what this arrow down here means. If you remember back, way back here, I didn't actually use that language, but arrow means the marginalization. So these are things that could be potentially joins down there. We consider such all possible things. And we say that a data subcomplex is said to satisfy this thing called a strong join condition if whenever you have two tables where you want to merge the attribute lists, and you have tables over each one of those original attribute lists which agree on the intersection, then you contain all the possible joins. So in other words, one way of thinking about this is the way to make in fact, I'll define it in a second. The way to make a data subcomplex which satisfies the strong join condition is to take all the data tables you found that fell off the back of the truck and have a strong command of how to run the inner join command in SQL and hit enter until you've done all possible joins you possibly could. And now you satisfy the strong join condition. Here's something neat. So let's get back to simplicial sets. So the nice thing about simplicial sets, if you haven't played with them before, is they give you a way to talk about homotopy without any pictures or geometry or topology. If you think the pictures I've been drawing are a total lie. I draw an edge between name and age. But again, if I draw an edge and I draw some geometry, I'm implying that there's some meaning to the points along the way. There is no meaning to being 1/3 of the way between name and age. But I want to talk about homotopy. The reason I want to talk about homotopy is I want to talk about structure. One of the things that simplicial sets allow you to do, and again, we really did learn this by reading Greg Friedman's wonderful paper, Elementary Illustrated Introduction to Simplicial Sets, is they allow you to talk about homotopy using only combinatorics. So we define what we call the kth horn of an n-simplex. What that means is if you take an n-simplex, thought of as a simplicial set, throw away the kth boundary face, and of course, therefore, also throw away all cofaces of that. That's the kth horn. So for example, and I think people can see my thing here, right? If I have a triangle, that's a 2-simplex, and I remove this thing with form of my 2 thumbs. So I remove my thumbs, and I remove the interior juice of the triangle, and I'm just left with 3 vertices on these 2 edges. That's a horn. And if my thumbs were the second edge, that's the second horn. We say that a simplicial set satisfies the con condition, and we don't, but these are the literature. If whenever you have a map from a horn into that set, you can get a compatible map, which agrees on the original stuff and then extends from the full simplex. So that sort of smells a little bit like homotopy. In other words, what this is really saying is if you have a triangle that you map into the space, and that kind of smells like a disk, if you have a map from sort of part of the boundary of the disk, which is sort of the horn is playing the role of part of the boundary, you can always kind of shove it past the triangle over to the other part of the boundary. So that looks like a homotopy, but it's just phrased entirely in terms of combinatorial language. The thing that the con condition gives you, and I should have put this in here, but just to sort of not sure who knows what and what backgrounds we're coming from, is that when you satisfy the con condition, you can define a simplicial homotopy. So if X satisfies this condition, then there is meaning to talking about pi3 of X, where X is the simplicial set. It actually has some meaning. Okay, so the first fundamental theorem, and this is the one that was quite difficult to prove, says if I have a data sum complex, which again is a simplicial set structure, but augmented with that notion of merging of this ambient thing, if it satisfies the strong join condition, then it satisfies the con condition of the simplicial set. So in other words, if whenever you have 2 tables which agree on some overlap, then all possible joins of those tables are already in your collection, then you satisfy this con condition. And the proof is just bloody and horrible and constructive. As in, you hand us a horn and we sort of show you how to make the thing. We very strongly suspect this condition is if and only if. Right now, we can only prove a slightly weaker version of the converse, and it doesn't matter for any of the applied math we're doing, so we stop thinking about it. But we think this is, we have no reason to believe this is not if and only if. We can prove a slightly weaker version of the converse. So what does that mean? That means that as long as you satisfy the strong join condition, you can talk about the homotopy groups of your data subcomplex, which is really neat. And all of a sudden, you can apply all of the theory. What's kind of nice about the sort of evolution of this problem is at the beginning of the problem, we were like, cool, if you have homotopy, Steenrod gives you all these things, you can add persistence, it's going to give you all these things, it's going to work out fine. It took about 1.5 years to sort of make homotopy happen, because we didn't realize the simplicial sets was the right language. Okay, so let's make a new definition from a data engineer perspective. Suppose you hand me a data subcomplex off the street. So what that really means, I do a bunch of surveys, I have a bunch of data tables. and I consider faces and degeneracies and things like that. So that's just the data I have on my desktop right now, the tables. I'm going to define the complex of perfect joins, script f upper 0, to be everything that can be generated from it by joining stuff. So really that literally just means do as many join commands as you possibly can until your finger gets tired hitting enter on SQL or whatever else you're doing. The script, the not in the script f sub not is meant to be evocative. It'll be replaced by a script f sub t when we start doing persistence. So the mathematician perspective is that as long as you do that, you can talk about homotopy. Okay. So it's not really a lemma, it's really just unraveling the definition. But if I have a simplicial map from the boundary of some cell downstairs in my attribute simplicial set into this space of perfect joins. So what does that really mean? I have age, name, weight down here. If I have some way of saying a section that goes all the way around the circle, age, name, weight, down we go, that defines a class, alpha f, in pi n minus 1 of f naught. Why does it? Well, the boundary of delta n is an n minus 1 sphere, and a section is therefore a map from the n minus 1 sphere into f naught. So I can look at its homotopy class, which I'm allowed to talk about because of this con condition. I can look at its homotopy class, and there it is. Moreover, that class is the identity in homotopy if and only if you can do the extension. So this is the beautiful thing of obstruction theory. If you think about these, for example, think about vector bundles for a second instead of all the simplicial set nonsense, right? If I have a vector bundle over something, and I have a map from the boundary of a two-cell, a section upstairs, if I can extend that section onto the interior of the two-cell, that's exactly the same thing as saying that that map is trivial as an element of pi 1 of the fiber, right? Because the extension gives you the smushing to a point, or whatever and if you can smush it to a point, that also gives you the extension, right? So that's Steenrod's big insight in obstruction theory. Cool. So now what we can do is we can make this, we can define what we call the obstruction cocycle. And again, if you've seen obstruction theory here, if you believe us that the simplicial set and the con condition setup allowed you to talk about vector bundles talk about the same kind of ideology as vector bundles, you can turn off your brain here and just think about vector bundles. So if I have a data subcomplex of subambient data complex, and I have a simplicial section downstairs, so that's again the picture I had there, then the following are equivalent. If I can extend the thing to the next skeleton, or whenever I have the boundary of an n cell downstairs, I include that into the skeleton, I map it forward by the section, I then just include that into f naught, that whole composition is the identity on the homotopy. So in other words, this is this thing called an obstruction cocycle. If I have a section downstairs on the n minus 1 skeleton, I can define an element of C upper n of the upstairs data subcomplex with coefficients in pi n minus 1 of f naught by just simply saying what is an element of C upper n? It's a group element for every n cell downstairs. So if I look at an n cell downstairs, what do? I say, what does the section do to you on the boundary? I know that's defined because I have a section on the n minus 1 skeleton. I then look at that section as an element of pi n minus 1 of f naught. That's my element of pi n minus 1 of f naught. I've made that assignment to every n cell. So I have a cocycle. Turns out that it's a cycle. That's one of the things Steenrod proved. I have a cocycle of dimension n doing that. Okay. So that's neat. Okay, so now here's the sort of the thing we were sort of wishing to do for a year and a half, which is we knew sort of obviously that if you had obstruction theory, you could make things persistent in a nice way. And we then had to set up the right sort of model. Okay, so the last theorem says, if you want to know whether you can do a global merger, or a bunch of local mergers, you set up this obstruction theory and then you just compute this cocycle, and that tells you some stuff. Cool. Suppose we want to do approximate merging. So in other words, right now, if I look on the left, I can't, if I have my local mergers, which have merged age name and name weight on name weight and weight age on weight, and so on and so forth, I cannot do a global merger. I'm doomed. But if I'm a little bit less uptight, people lie about their weight all the time, and I say that 182 and 200 are the same, sure they are, then I can. Right? So how do I how do I make a statement that says, as long as you're willing to say that 182 and 200 pounds are the same, go for it. You got it. So here's the new definition. If I have a data subcomplex, so that's all the data I currently have. And remember, script f sub naught was all the tables that I can make by just joining everything in sight. I'm going to assign script f sub t to be all the tables upstairs, so all the tables that are within t in Wasserstein distance from being joins of tables that I currently have. So in other words, another way of saying that is, what does it mean to be a join of table I currently have? It means a table on some joined attribute list where when I marginalize it down, I get the right answer of my tables. And remember, tables are measures. Okay, so what does it mean to be almost a join? It means to be a table on my joined attribute list so that when I marginalize it downstairs, the Wasserstein distance between the marginalization and the correct answer is no more than t everywhere I check. That's my definition. The theorem is that this is still a simplicial set. It's a little bit long, but it's all just bookkeeping. Nothing is hard about that. You just sort of check that if you check the Wasserstein distance goes a particular way when you do things like face and degeneracy maps. And so now you see where the persistence is going to come in. So if I have a data subcomplex downstairs sitting within all of the data that I possibly have, and I take two parameters, t less than or equal to q. Obviously, if you're within t of being a join, you're within q of being a join, because t is less than or equal to q. That gives me my map on pi n minus 1 of ft into pi n minus 1 of fq, which therefore gives me my map on these cocycle groups. So whenever you have a section downstairs, what I can say is for any particular value of t, I get this obstruction cocycle at t. The nice thing about this sort of thing is that as you map it forward, it's sort of obvious to see that it only becomes 0 once and then it's 0. Right? So you sort of say, it's a nice way of talking about language, right? The idea that here is an attempted merger. This merger is not currently possible, but if I allow a little bit more approximation like Wasserstein, which is really morally equivalent to saying 182 and 200 pounds are the same weight, right? That's really what we mean by this approximation. All of a sudden, mergers do become possible, right? And so therefore, the cocycle becomes 0. We phrase this in what we call the second fundamental theorem for data subcomplexes, and this is this is 4 lines. It's basically Steenrod's trichotomy translated to a little bit of persistence and modeling. But it's, I think, much more interesting to people who care about the problem at hand, even though it's much easier to prove. The first theorem is really setting up the language. Given a section and given a notion of tolerance, exactly one of 3 things is true. Either this cocycle is the identity as a cocycle. So in other words, we're not talking about cohomology yet. It's just a cocycle. But it's a cocycle which assigns an element of a homotropic group to every cell. That means that all those homotropic group elements are the identity. That means I can do my extension at least within tolerance t. Cool. Maybe it is not the identity as a cocycle, but it is the identity as a cohomology class. Then there's this thing that Steenrod came up with called the difference cochain, which I had a longer time I sort of go into. But this really pretty thing says, basically what happens is that you can do the merger, you just screwed up at the last level. So what this really means is that, and we have this paper and I haven't put it in the slides, and I really should, is that if you've merged things up to level n-1, you've done a bunch of local mergers. Now you can't merge it at level n. But if you're in this category 2, what this tells you is you can keep your mergers down to level n-2 and just fix it at level n-1 in a way this thing called the difference cochain tells you how to do. And then you can proceed. So if you really think of these as branch offices and regional branch offices and super regional branch offices, it means the regional branch office screwed up, but the branch offices did fine, right? Like that's the idea. Or you're not the identity, even as a cohomology class, in which case you have to increase the error threshold to make any progress. It also enables you to give these nice notions for every possible code section. We can just define the persistence of how much of a global problem it causes, which is just how much you have to thicken to make it not a problem. A thing we're writing a paper about now is usually when people do joins and fusion and things like that in the kind of multimodal fusion world, they think about when you try to fuse things, you think about setting, there's lots of ways you could fuse them. Each one might have some sort of cost function, which you might want to do backpropagation on or something silly like that. What you can do here is say that if you have a bunch of different local fusion problems, if you have a new local fusion problem, you can assign a cost function, which is some weighted combination of some local loss function, which is not up to me, but also something related to this, like e to the minus t of sigma or something, which says this looks like a really nice local fusion, but it causes such a big global problem that you would have to mess everything up to some level t. So buyer beware. And so we're trying to sort of show that that's a useful way to think. Parting thoughts, just again, if you have what humans call a data table, we think of that as a particular version of one of these things just by sort of atomic measures. Obviously, compact and finite spaces are all you're ever going to think about. This notion of an attribute can be very, very general. You can also take a list of attributes and consider that as a single attribute. In other words, these notions of summarization. Everything we're doing so far uses L infinity, and we're sad about that, and we don't know how to prove things otherwise. That's sort of the whole. And right now we're trying to implement it. There are some things that are obvious and some things that are hard. So I'll stop there.
Okay, thank you. So I would invite everyone to unmute themselves and clap for Paul for his wonderful talk. Okay, so now it's time for questions.
So, hi, thanks for the talk.
Of course.
So it seemed like you were defining whether or not a merger was, quote, possible, sort of based on the actual scalar values of the data set. But like, of course, we can do an inner join that would lose data because there would be SQL nulls.
Right.
But I was sort of just trying to understand, and then that could be like, in doing an inner join that loses data is definitely a totally valid thing to do in some circumstances. So how do we know, like perhaps do we use that, like in the very end, you were talking about how we can put some sort of measure on how costly it is to, to join these two or not. So maybe like we could set a cost and say, okay, but if it costs more than this, then maybe we should lose the data and just, have some SQL nulls, and or they wouldn't be nulls because the rows are just lost. But like, how do we have you thought about that at all? Or
I'll confess I haven't really thought about that, but it's a very good question. Two glib responses, which I don't think are adequate, are one, you could talk about that local global cost, as in like, here's how much it costs you to delete a row or something. There's also declaring the metric space at the beginning, right? Remember that each attribute list has a sort of declaration of what heights are allowed and how far is 5'7" from 5'8". That's up to you. I think you could probably do something like we do in persistence, where we define the cost of sweeping something to the diagonal, and maybe just define the cost of deleting entries. I think that should go through. I'm not entirely sure, and that might get at what you're doing. But yeah, that's a really good point. And I think we should, if there's an obvious way to just think about that, we should just say that. Yeah, because I think data nulls are exactly what you don't want, right? But you can do it and make the join happen, and so SQL nulls. And so I think you can incorporate that into the cost or the metric, and I should just think of the right way to do it. It's a really nice question.
Hey, I have a question.
Of course.
So I was wondering, when I think about database joins, like I don't typically think about joining on measurement values. So like I can't off the top of my head think of an example where I want to take two tables and join on height or join on weight really. So I was wondering, what are some examples where these sorts of mergers come up naturally in a way where somebody might intuitively understand, yeah, this is a real world scenario where, I guess I'm not really seeing the example you had as a real world scenario. So I was wondering if you had some other ones.
That's good. Maybe it's a different perspective, but I mean, I think all the time of like, okay, I have you know, I have these students in this particular list. I like joining on a particular column makes a lot of sense to me, right?
Yeah.
So if my columns, so what I mean when I talk about attributes, like attributes, think of them as literally the column labels in like an Excel spreadsheet or something, right?
Exactly.
And so I guess to me, it makes total sense to say I have height, weight, and shoe size. And over here, I have weight and blood pressure. And I want to merge these two on weight.
Like we'd have no, just because two weights are the same, we don't know that those actually correspond to the same person.
Right.
So like,
so the unique key thing.
Right, exactly. Yeah. So often joins are going to be, you know, I have my customer list over here and my orders list over here, and the orders list has a customer ID in it, and I want to match all my orders, you know, want to figure out which orders match to which customer.
That makes total sense. I think right. So there, the idea is that whether you want to, I think that's something coming from outside the problem, but it's totally valid, is that you might have some unique key, which is sort of saying these are the, right, because nothing what we're doing here, like you could get totally fooled here to say that if there's someone else who's 200 pounds, then this could map through totally fine, right? And of course, there might be many people who are 200. So I think that, yeah, that's a weakness there. I think this is maybe most useful, honestly, when you're trying to merge things where you don't have unique customer keys. Is that a satisfying answer at all, Rachel, or does it still seem like a hole?
Well, so I'm trying to think of another example. I guess I can imagine, like, say you've got all your students and you've got their grades.
Right.
And then you've got another table where grades is an attribute of it, like scholarships they might be eligible for.
Right.
And then maybe you've got another thing where, you know, you've got the student and the schools they've attended. And, you know, I can kind of almost imagine like, more of like a binning issue where maybe you have the actual measurement is in terms of a number, like say their score in 100%, versus over here, you've got A, B, C, D. Those could be like bins, right?
Yep.
Maybe that's sort of what's going on there. But like, yeah, merging on like an exact weight between two people, I'm just like, I can see it, but it doesn't feel real. But I think, you know, this idea of moving from one scale to another across tables, maybe that's sort of.
That makes a lot of sense. I think that's sort of what was buried in what we were doing with the thing I skipped over with the inclusions. That as long as you sort of, the way you do your inclusions is that you declare that this grading with this scheme here and this grading with this scheme are included in the same way, and you say how the translation happens. Then I think everything maps through.
Okay.
So cool. That's a really good question. I'll talk with Dave about the right way to phrase and maybe even email back.
Yeah, just because like the example you have in here, I mean, it was easy to see and it was illustrative, but to somebody who works on databases with data all the time, it just didn't really feel real.
Right. No, that's very helpful.
Cool. Thank you.
I have a question.
Yep.
So computing homotopy groups is not, I mean, it's not very computerizable, right? So is there a way of maybe like weakening, linearizing?
That's exactly what that's the one thing that's the big gap right now. It is, we think, the case that in a lot of examples we're doing that as soon as you thicken to a certain amount, the homotopy groups of these F sub t's are pretty simple. And so we think there's sort of a way to kind of cheat at it and just say, okay, this is a decent approximation of it. But yeah, no, that's the big obvious gap right now. It's not just runtime, it's that the fact that some of them aren't known, right? And so yeah, and you know, one can always try, you know, there's always the dodge that just compute homology groups and, you know, get some contrapositive type results or something like that, which might be what we fall onto. You know, and just, you know, if this isn't zero, then that isn't zero, right? And think of maps from homotopy to homology, things like that. But those are design choices we're thinking about now.
Right. So yeah, you would get an obstruction. If the obstruction is non-zero, don't even try it. Otherwise, try some of the standard algorithms.
Yep.
Yeah, or maybe like, yeah, know where it's going to fail, so I don't know, you can do something else there.
Right. I mean, honestly, this is a thing that we never say out loud, but right, when we do persistent homology, what we actually want to do is figure out whether things are homeomorphic, but good luck computing that, right? So we often use homology as a shadow of homeomorphic.
Right. And then Kant complexes are often immense. Like the Kant condition kind of forces you to have lots of non-degenerate simplices.
I mean, they're infinite, right?
Right. So if I understood correctly, you never like have the full Kant complex or expect to have a full Kant complex in your computer, right?
No, you're just going to, again, we're figuring it out for the computability, but I think as long as you have essentially the generators, the non-degenerate simplices, I think that's going to be enough to be able to do what we want to do.
Right. Okay. Yeah, I'd be curious to see the algorithms that come out of this. It sounds really interesting.
Yeah, we find it interesting too. I can't. I am hoping this year it comes out. We're not sure yet though.
Thanks.
So I think there could be like a sort of machine learning-ish application to the binning idea we were talking about earlier, where sure, it's not like we're not by saying, you know, this person weighs 200 and this person weighs 201 and this person weighs 199. Of course, we're assuming they're not the same person. We know they're not the same person, but when we define, like basically defining our metrics is going to define how big our bins are, and we can do a bunch of joins and we end up with sort of these multi-dimensional bins, and then we say, okay, everyone in this group belongs to like, you know, this category of people, you know, maybe we'll advertise to them, and everyone in this group is this category of people, and we advertise to them. We'd have to have a way to sort of delineate the bins, because now we have multiple dimensions. Each thing we joined on would be like a new dimension. We have to have a way to figure out, well, I guess there'd just be a bunch of like sort of highly overlapping bins that we could then sort of, you know, draw conclusions about and have some practical application for.
That's a really nice suggestion. I mean, I think it's the only thing I'll push back on there a little bit is that I think what you're saying is exactly right. At least in my motivation, I was thinking there certainly is a chance that the person who's 200 here and 198 here is the same person, right? Like because I think like my mom, when she goes to the doctor because of various like standing problems, depends on what scale she's standing on, it's going to give her a different weight, right? And so you can see things in that issue as well.
Yeah, and the problem is, I guess, if your data set's too large, you could have a lot of people that are about that weight, and that's when you would lose the information.
Exactly.
Further questions? I'll ask one more question, Paul. So I was struck by your results. Sort of, you're looking at level n if a merger is possible, and you look at these homotopy criterion, and either it is possible or you only have to fix the n-1 level. Right. So and I can sort of see how this is coming out of obstruction theory, but I'm trying to wrap my head around what if there was a mistake at the n-2 level. In this framework, would that have implied that the merger already at that n-1 level?
That's exactly it. Yeah. So that is the, and that's back in the sort of classic Steenrod on vector bundles. That it's if the fact that we've gotten to the n-1 meant that we did the mergers from n-2 to n-1. But those can, you know, you go down a blind alley and then you can't get the next one. Yeah. So the nice thing about that difference code chain is that it tells you only have to go one level down and correct it in a way that tells you how to correct it. But I think to Rachel and sorry, I'm trying to read the name, Alyssa's point is that I think even there, that correction might not be the most pleasing in sort of a database sense that we don't know yet.
It's great how this all fits in combinatorially as well using the central section. Any final questions? Well, if not, thanks so much, Paul.